Eruptions at Wizard Island, modeling potential rock fragment ejection scenarios in Crater Lake, Oregon. Let's begin with the location. Wizard Island is a 2,000-meter tall volcano sitting in the deepest lake in the United States, Crater Lake. Crater Lake was formed after the eruption of Mount Mazama 8,000 years ago. For this project, as you can see in the top right corner, I'm only going to be focusing on the western wall of the caldera, as well as the tippy top of the cinder cone that rests above the water. The purpose of this project is to experiment with 3D GIS skills in a potentially real-world scenario. While there is not expected to be an eruption in this area anytime soon, I think that it's useful for researchers and planners to investigate the natural hazard risks in the region anyways, before they occur. My objective in this project is to create an approximately 15-second video in Unity using rigid body physics and particle systems to represent volcanic eruptions in a mechanistically accurate display. I also want to analyze the interaction between pressure and direction in the ejection of rock fragments and identify the landscape interactions with these different eruption scenarios. My methods in this process involved many apps and platforms, as well as many hours, and I've organized my workflow into this graph, and I'm going to explain it to you now. My data source for this project was open topography. I selected a point cloud of just Wizard Island and the western wall of the caldera. This next step involves me converting my mesh into solid geometry. I did this in Blender. I put my FBX mesh into the middle of Blender and I put a solid cube within it and extended the sides to meet the mesh's sides. Then, I selected the cube and performed a Boolean intersect function. Next, I had to bring my solid geometry into Rhino so that I could use the plugin called Grasshopper. That's what the second picture on the screen is. So, I had to place a mesh on the board, connect it to a 3D populate function, and then connect it to a Voronoi function. And then I had to put a counter, not showed on the picture, but I set it to 100 so that when I baked the Voronoi, my 3D geometry was converted into 100 fragments. These fragments were exported as FBXs and used for my volcano. So I brought my split fragments back into Blender because they looked similar to the red box in the corner there. They were all connected and they didn't have the shape of the volcano at all. So I needed to perform another Boolean intersect operation to split the rock fragments into the shape of the volcano. I was having a hard time. This required a lot of trial and error. I ended up having to do a Boolean intersect on every single individual fragment. But the outcome was beautiful. And as you can see, in the last and second to last pictures there, my volcano was split up awesomely. Circled in red is the commands that allowed me to adjust the strength and the distance that each of my rocks flew before they interacted with the particle system. This included magnitude, time that magnitude was applied, and as well the direction, which was either up, down, or forward. I added some visual effects to make my simulation look realistic. All of my rocks had mesh colliders. Most of them had rigid bodies, so that they would interact with the mesh collider of the caldera wall. However, the water didn't have a mesh collider, so the rocks would just tend to fall down and sink into the water. I also added a lava effect. That was just a sphere with a lava material on it with no mesh collider, so it didn't get in the way of any of the volcano eruptions. This is an overview of my options, with screenshots at 5 seconds and 10 seconds into them. I ran 3 rounds of simulations, all with different permutations. Round 1 was a lateral blast, round 2 was a vertical blast at low pressure, and round 3 was a vertical blast at high pressure. I controlled the pressure by applying different emissions of particles. Upon analysis of my visualizations, I can conclude that areas within the caldera are at the highest immediate danger of ejected rock fragments, and that the caldera will contain most of the ejected rock fragments within its walls because of its height. Evacuation of the area will be necessary, and development within the bounds of the caldera and even above the scar should not be permitted. The most dangerous eruption type in this case would be a high-pressure lateral blast, as it will interact the most with the surrounding topography and probably result in the most damage. Thanks for watching. I hope you enjoyed.